Why is a theory of everything the holy grail of physics? What is everything? I'm Robert Lawrence Kuhn, host of Closer to Truth. Recently, I had an in-depth conversation with Michio Kaku on his new book, The God Equation, The Quest for a Theory of Everything. We explore some of the biggest questions in physics and cosmology. What happened before the Big Bang? What lies on the other side of black holes? Is time travel possible? Are there wormholes to other universes? Are there higher dimensions? Is there a multiverse of parallel universes? Why is there something rather than nothing? Has Michio surprises in store? Closer to Truth publishes videos on cosmos, consciousness, and meaning every day. Watch them by subscribing to this YouTube channel and become a member of closertotruth.com. Michio, it's great to see you. Congratulations on the book, The God Equation, The Quest for a Theory of Everything. Now, as you and I like to do, I'm going to go through each word and get your sense of it. First of all, on equations, I certainly know what an equation is. God, I assume we'll talk about later. Quest, you and I have both been on a quest our whole life. Theory, we know, but I want to focus you on what does it mean, everything? When you say a theory of everything, what is everything?
Well, there are four forces that govern the entire universe. We find no exceptions to gravity, which holds us onto the floor, keeps the sun from exploding. We have the electromagnetic force that lights up our cities. And then we have the two nuclear forces, the weak and the strong forces. And we want a theory of all four forces. Remember that all of biology can be explained by chemistry. All of chemistry can be explained by physics. All of physics can be explained by two great theories: relativity, the theory of gravity, and the quantum theory, which summarizes the electromagnetic force and the two nuclear forces. But to bring them together, that would give us a theory of everything. All known physical phenomena can be summarized by an equation, perhaps no more than 1 inch long, that will allow us to, quote, read the mind of God. And these are the words of Albert Einstein, who spent the last 30 years of his life chasing after this theory of everything, the God equation.
So what are the specific areas? Because there's been a criticism that when people hear the word everything and then go through the hierarchy of the sciences, which you just did very nicely, starting biology and then the chemistry and then the physics and then the laws of physics, that sounds like a very reductive approach to reality, that all reality can be reduced down with that emotionally tinged word to the primary forces, whether we know them now or more fundamental. But that leaves the question of are there laws at higher levels that are emergent? Indeed, a kind of strong emergence where they are, in principle, not predictable from lower level laws.
Well, I like to think of this quest as a chess game. Think of a cosmic chess game that lasted for the last 2,000 years, where initially we work out the theory of pawns. We begin to reduce the motions of pawns down to certain discrete rules, how the queen moves, how the king moves, but that doesn't make us a grand master. Mm-hmm. That doesn't make us a master of these things. And strategy, where is strategy in the laws of chess? Strategy is a byproduct of the laws of chess. So what I'm saying is what we physicists are doing is trying to find the rules of the game. That doesn't mean we're going to be grand masters of strategy. Strategy is not within the rules of chess. It's a byproduct, as you pointed out. And that's why emergent phenomenon, that means that we will still have a job. People ask me the question, Professor, if you find this equation, are you going to be unemployed? Will you be out of a job because you've reduced everything to one equation and that's it, folks? No, because we still have to become grand masters of the rules of chess. We have to understand emergent phenomenon. intelligence, the soul, love. These are probably emergent phenomenon. All I'm saying is we physicists want to get the rules of the game.
To continue with the analogy, and all analogies, of course, are limited. In chess, once you know the rules and you're looking to strategy, that imposes a human mind on the process, some interaction between the laws and a human mind. But when we're dealing with emergent properties of the way the world works, whether at level of biology or even lower level chemistry, you don't necessarily need some conscious agent to make that emergence happen.
Well, even in the rules of chess, we have chess playing machines with artificial intelligence that can beat human grandmasters. So there's nothing necessarily unique about human consciousness and the theory of everything. I like to think of it this way. I like to think of it when I was a child, learning about physics, that on the other side of the galaxy, there's an alien out there struggling with the same equation, the same rules, the same understanding of the physical forces, but in a different notation. And then I began to realize these things are beyond human consciousness. Alien consciousness throughout the galaxy will eventually discover the same equations that I'm struggling with right now with a different notation. And so then I began to realize that these laws are universal throughout the universe. Now, Shakespeare could be great. We have so many great products of the human mind, but they are products of the human mind. An alien on the other side of the galaxy wouldn't make heads or tails of what's being done here on the planet Earth. And that's why I think this theory is universal, beyond human consciousness, even beyond reductionism, because we're now getting the entire ball of wax explained by one theory.
You've talked about some of the big questions in physics and cosmology, which could lend themselves to greater insight once the 1-inch equation, as you put it, is realized. What happened before the Big Bang? Is there something on the other side of black holes? Time travel you've talked about. Wormholes to other universes, higher dimensions, multiverse of multiple universes in the same space, or even parallel universes in different dimensions. How would the theory of everything impact on those big questions in physics and cosmology?
You know, the strange thing is that Einstein's equations of general relativity allow for time travel. They allow for gateways to other universes, like a looking glass in Alice's Looking Glass. It turns out that these are solutions of Einstein's equations, and Einstein himself had to grapple with this possibility. But the question is, are these realistic? It turns out that the energy necessary to build a time machine is that of a black hole. And are they stable? Once you enter the wormhole, the gateway to another universe, will the machine explode? Stephen Hawking thought so. But you see, that's not definitive, because we're only using Einstein's theory, which we know break down at what is called the Planck Energy. When people talk about the laws of physics, they talk about the laws of physics only up to the Big Bang, that is, the Planck Energy. It turns out that you need a theory of the Planck Energy to calculate whether or not a time machine is stable or whether it blows up the minute you walk into it. And this is where something called string theory comes in. You see, string theory is the only theory that can unify all four of the fundamental forces, including gravitational corrections, and you can calculate whether or not the time machine is stable or unstable. And the same thing with wormholes, the same thing with higher dimensions. All these are consistent with Einstein's theory, but they may break down if quantum corrections make the thing explode. So Stephen Hawking, for example, finally concluded that yes, gateways to a distant part of the galaxy, wormholes, may be possible without quantum corrections. But time machines may blow up once you enter them. But this is where you see the quantum theory comes in. Because in the quantum theory, if you go back into the past and change the past, the timeline splits in half. So that if you go backwards in time and save Abraham Lincoln from being assassinated at the Ford's Theater, You've saved somebody else's Abraham Lincoln. Your Abraham Lincoln did necessarily die, because in the quantum theory, the river of time can split into two rivers. One river is your river, in which Abraham Lincoln did die. Nothing can change that. But the other river is the river where Abraham Lincoln survived Ford's Theater. This is the many worlds theory, the application of the quantum theory to time travel.
But that makes you committed to the multi-world interpretation of quantum mechanics, and that is controversial, to say the least.
That's right, very controversial, because it means that our universe is a bubble of some sort. We live on the skin of the bubble, and the bubble is expanding. That's called the Big Bang theory of Einstein. But theories like string theory, inflation theory, says that there could be other bubbles out there, other bubble universes, that when universes collide, two bubbles merge to form a big bubble, or one bubble can fission in half. This is the Big Bang. The Big Bang is either the collision of universes or the splitting apart of universes. And so we have a multiverse of universes that are being born even as we speak. Even as we're conducting this interview, universes are being born in another dimension. And then, of course, children ask the next question. If you have all these bubbles, then what is the universe expanding into? If the universe is everything, then how can everything expand into anything else? Well, the answer is, if our universe is a bubble, a three-dimensional bubble, it means it's expanding into hyperspace, a higher dimension. That's what the universe is expanding into. And who knows, maybe we'll bump into another bubble one of these days.
Yeah, that would not be good news if we didn't. Look, but I think we're talking about a multiverse, but there are different kinds of multiverses that were embedded within in your discussion. One is the branching out of other bubble universes from our universe, which are directly related to the theory of inflation for our universe. If you're going to have inflation to explain the problems of the Big Bang in our universe, then by natural extension, you seem to have these infinite universes bubbling off. But that's very different from the multi-world interpretation. They both yield to different multiverses in reality, but they're radically different. You could have nesting of one within the other. But the multiverse, the multi-world interpretation of quantum mechanics is a specific so-called realistic approach to the wave function that says it doesn't collapse, it branches off, and it yields, if not infinite, virtually an infinite number of branches in an exponentially growing fashion beyond comprehension. That strains my sense of credulity about reality.
Well, you see, reality exists independent of our wishes, independent of our will. It is what it is. And the bottom line is experiment. You see, science is based on things that are testable, reproducible, and falsifiable. That is what we call science. And of all the theories that have been proposed, one theory which does stand out and is compatible with experiment, and that is the inflation theory, the theory that we had a turbocharged explosion at the beginning of time. But you see, that inflation theory is a quantum theory, which means that given enough time, there's a probability that it will happen again and again and again. So once you impose the quantum theory on the explosion that created the universe, you necessarily have a many worlds interpretation. You have no choice. Embedded within the quantum principle is the idea that if things can happen, then perhaps it does happen someplace else in the universe. Right. And the next question you're going to ask me is Elvis Presley still alive in a parallel universe? And the answer is, well, yes, the king could still be alive in a parallel universes, because these universes span all possible universes.
Are you then equating the scientific confidence that we have, which is not total, in inflation theory, because there are different views on that too. But that is generally considered sort of the standard model of cosmology, has inflation embedded within it. But I don't think the multi-world interpretation of quantum theory is at that same level of confidence.
Well, put it this way, there is no experiment that you can devise to contradict the many worlds theory. In fact, there are several different interpretations of quantum mechanics. The other alternate interpretation is the Wigner interpretation, because every experiment has to have an observer, but who's watching the observer? Somebody has to watch the observer, but who's watching the observer watching the observer? Well, another observer, and then you have the spiral of observers watching other people observe the observers of the other universes, and the whole thing requires God or a supreme being. And Eugene Wigner, the founder of this alternate theory of quantum mechanics, ultimately believed in Hindu mysticism. Now, I personally would prefer to have the multiverse theory than Hindu mysticism, but that's where the alternate theory of quantum behavior exists. If you don't believe in the many worlds theory, the other major belief within quantum theory is Wigner's friend, this infinite sequence of observers until finally you come up with infinite consciousness. I would prefer to have many worlds.
Okay, Michio, let's now get into the big part of your book, The God Equation, The Quest for a Theory of Everything, in terms of understanding what this theory is and could be. So let's start simply. What are some of the kind of structural things that you need to see in a final theory? I mean, you've used words like simplicity and symmetry and beauty and elegance. How do you organize those words? They're not quite synonyms.
Well, this journey goes back 2,000 years, back to the Greeks, who asked the question, what is the world made of? We had two competing theories 2,000 years ago. One was the theory of atoms by Democritus. A means cannot, tum means cut, atom means that which cannot be cut. But there was a rival point of view by Pythagoras, a Pythagorean theorem. He noticed music, the fact that lyre strings, when they vibrate at a lower frequency if you have a longer string. And he went by a blacksmith shop and he realized that metals that are being pounded by a blacksmith vibrate at a lower frequency if the piece of metal is longer. And he said, aha, that is the paradigm rich enough to explain the diversity of everything in the universe. And that metaphor was music. Music is the metaphor because there are so many mathematical ways in which you can write octaves and thirds and fifths and harmonies and G flat and E minor. Music represents the paradigm for the universe. Well, neither theory went anywhere for 2,000 years. The Roman Empire fell apart. The world was plunged into darkness. And over the centuries, we finally came up with chemistry and then a theory of atoms. But we now want to know why we have so many particles when we split apart all these atoms. Where do we make sense of all these things? And this is where symmetry comes into the picture. You see, we physicists believe in beauty. But what is beauty? Beauty is so ephemeral, so difficult to define. Beauty to a physicist means symmetry. It means you take a sphere or an ice crystal and you rotate it, and the object remains the same. And this means that your fundamental equation of particles, no matter how many particles you have, the equation should remain the same if you reshuffle them. And so our universe is symmetrical because you can rotate all the particles of the entire universe and the theory remains the same. And so symmetry becomes a guiding principle. And that's also the principle of music. Music has a symmetry when we talk about octaves and we talk about thirds and fifths. So we now have a new paradigm emerging, and the latest version of this is called string theory. Now, string theory says that subatomic particles, like electrons and neutrinos, are nothing but musical notes on a tiny, tiny vibrating string. So what is physics? Physics is the harmonies that you can write on these strings as Pythagoras believed 2,000 years ago. What is chemistry? Chemistry is the melodies you can play on this. Well, what is life and DNA? Life and DNA would be a string quartet, ATCG, the four nucleic acids of DNA, four string quartets. And then what is the universe? The universe is a symphony of strings. And then what is the mind of God that Albert Einstein spent so much puzzling over? The mind of God would be cosmic music resonating through hyperspace.
Why did Albert Einstein fail when he was seeking this unified theory for the last multiple decades of his life?
Well, I can read his works now, and I can see all the dead ends that he went into. And the fundamental reason why he failed, because back then in the 1920s, 30s, and 40s, we didn't understand the nuclear force. The nuclear force was the one force that eluded Einstein. He couldn't grapple with it. He had a good understanding of gravity. He had a good understanding of relativity and of the electromagnetic force, but he was clueless when he came to the strong nuclear force. And what the strong nuclear force is strings. Strings are the binding force that bind the quarks together, and we use the same language of springs to bind the entire universe together as well. So in other words, Einstein was ahead of his time, so far ahead of his time that he didn't understand what would come out of the nuclear force. And what comes out of the nuclear force is things like strings.
Okay, let's look at the flow of humanity's intellectual quest to get to this final theory. Now, you gave me basically the bookends. You gave me Pythagoras and the theory of resonance and music and vibrations, and then you jump to string theory, which I know you are a supporter of and a researcher in your career. That's string theory is controversial. We know that. But what I want to do is go through the steps that humanity has taken from the original thought, and especially as science began just a few centuries ago in a more serious way. And so when electricity and magnetism, the Faraday and did their discoveries, then I want to start with Maxwell's equations, and then very briefly go through these critical steps from Maxwell's equations to Dirac and the electron to quantum electrodynamics, and then quantum chromodynamics, which deals with, of course, nuclear forces, and then, as you would see it, to string theory, because it wasn't just jumping from Pythagoras to string theory, although I can see the connection.
Well, let's now fill in all the missing steps. We started with Newton's theory of gravity, which was formulated in the 1600s. In the 1800s, light was then finally worked out as a consequence of a symmetry between electricity and magnetism. It was Michael Faraday who first realized that a changing magnetic field can create an electric field, and a changing electric field can create a magnetic field. That's the basis of dynamos. That's why we have vacuum cleaners. That's why we have modern society, because electricity and magnetism turn into each other because of a symmetry. They are symmetrical twins of each other, giving us what is called the electromagnetic force. Then, after the nuclear force was finally unleashed with the atomic bomb, in the post-war era, people began to seriously look at the nuclear forces. And we began to realize that the equations of Maxwell, the equations of electromagnetism, have to be generalized. Light has a partner that was missing that Einstein failed to see. The partner was called gauge particles or Yang-Mills particles. These particles also exist in a symmetry with the electromagnetic field. So the electromagnetic field has, in some sense, a partner, a larger family of vibrations, and these vibrations are called gauge vibrations, and they in turn hold the electrons and the protons and the neutrons into atoms and into the nucleus as we know it today. So today, to fast forward, we now have the theory of almost everything. It's called the Standard Model. $10 billion have been spent building the biggest machine of pure science outside Geneva, Switzerland, the Large Hadron Collider. And what did we find by spending $10 billion on this huge, colossal machine? We found a theory called the Standard Model. It is the most successful quantum theory of all time. We see no deviation in that model. The problem is, first of all, it is one of the ugliest theories known to science. It's a theory that, quote, only a mother can love, unquote. It's like taking an aardvark and a platypus and a giraffe, scotch taping them together and declaring that to be nature's finest evolutionary creation, the end product of billions of years of evolution on the planet Earth. Nobody believes the Standard Model is the final theory. It has 36 quarks and antiquarks, 21 free parameters that you can adjust by hand, 3 identical carbon copies in generations of each other. It is a mess, but it works. So then the question is, are we looking at the tail of a lion? Einstein said that even if I see a tail, I know there's a lion connected to that tail. The tail is the Standard Model, the theory of almost everything, which neglects all of gravity, has this huge zoo of subatomic particles that seem to have no rhyme or reason, but it works. So far, nobody has come up with a successor to the Standard Model except string theory. Now, some people say that, well, maybe I don't like string theory. Give me an alternative. Well, there is none. It is the only game in town. Now, that doesn't mean it's correct. As Carl Sagan liked to say, remarkable claims require remarkable proof. Where's the beef? You have to have the proof. Right now, there's no proof one way or the other, but I think that proof is coming. In fact, that's one of the reasons why I wrote the book. New experiments with dark matter, new particle accelerators being proposed in Japan, China, and the European Union, new gravity wave detectors in outer space. These are new devices which are going to open up the post-Standard Model era. The Standard Model was too successful. This ugly theory was simply too successful for its own right. Now we're going to go beyond the Standard Model and subject string theory to the acid test. If it fails, then it will be just another corpse on the trail to the unified field theory. Yep.
Some supporters of string theory actually disagree, I think, with your stark proposal. And they say that even if all of these experiments don't work, there is still some fundamental consistency within string theory, its predictability, its internal consistency that is at a deeper level that your experimentation can handle. So, I want to know, do you agree with that? You know, even if these experiments, as you've articulated, maybe you need to have a collider the size of the galaxy to reach Planck level intensity and levels in order to prove string theory. So is it possible to validate string theory on the theoretical basis alone? And if so, what are those bases?
Well, let me say two things about that. First of all, we forget the fact that you don't need an atom smasher the size of the Milky Way galaxy to test string theory. You see, almost all physics is done indirectly. How do we know that the sun burns hydrogen? What do we know about the inside of a DNA molecule? We know a lot about the inside of an atom, the inside of a cell, the inside of the sun. We've never been there. Why? Because we look at indirect clues. Indirect sunlight from the sun allows us to determine what the sun is made of. Light from the stars allows us to determine what the stars are made of. We've never visited the stars. We've never visited the Earth. You don't need a direct test of string theory to prove it's correct. Second, if string theory can prove, for example, from first principles, calculate the mass of the proton, I think the game is over. If we can calculate almost from nothing the mass of a proton, the mass of the electron, the mass of the familiar subatomic particles we know today, I think it's game over. That'll prove that this is the final theory. You see, the theory of everything is also a theory of everyday energies. If we can calculate exactly the mass of a proton, the charge and mass of an electron, and so on and so forth, from first principles, I think that would be it. You don't necessarily need to explain every single aspect of the theory. You just have to explain everything about the world we live in today. At the present time, nobody can do that. There's not a single human on the planet Earth that can calculate the mass of a proton from first principles. If string theory does it, I think it's game over.
One of the claims of string theory is that in its normal operations and equations, suddenly you find gravity kind of popping out. So whereas in traditional physics without string theory, people are struggling with a quantum theory of gravity, bringing together general relativity and quantum theory, the claim is made in string theory it's a natural result of the equations as gravity pops out in the vernacular.
Well, I would agree with the thrust of that argument, the fact that in most theories, gravity is artificial. You have to put it in by hand. And when you do that, the theory blows up in your face. In other words, most theories hate gravity. Gravity is incompatible with most physical theories. But in string theory, as you pointed out, it's the opposite. String theory requires gravity. Let's say Einstein was never born. Let's say Einstein never created general relativity. General relativity emerges all by itself as the lowest octave of the string. Think about it. If Einstein had never been born, we still would have discovered the entirety of Einstein's theory as a byproduct of string theory, because all of Einstein's theory is nothing but the lowest octave of the string. But of course, the string has higher octaves as well that we can one day hope to find.
How does that literally work, where the lowest octave of the string is general relativity? I mean, that sounds nice, and I know it's mathematical, but give me an intermediary explanation between the raw equations and the simple assertion.
It's very simple. You simply take a vibrating string, the same string that Pythagoras played with 2,000 years ago, work out the lowest harmonics of the string, okay? And then you put it into what is called the action, the energy of the string, and you calculate the vibrations that you get. And the vibrations turn out to have spin 2 angular momentum, and is exactly Einstein's theory of gravity. Plus, as an added bonus, you get electrons coming out of it. And many unified field theory proposals never have electrons at all. These are theories of pure gravity without atoms. And so how can you possibly consider rival theories to be theories of everything? With string theory, you get electrons and gravity for free as the lowest octave of the string. Plus, as another bonus, you get higher octaves. And that's where we think dark matter comes into play. Invisible matter, which makes up most of the universe, in fact. We are the oddballs. Dark matter makes up most of the universe, and it's also predicted by string theory.
I'm going to do something very unfair, Michio. I'm going to put you as the prosecuting attorney for those who believe that string theory doesn't work and is a distraction for physics. And if you are in that role as the prosecutor, what are the arguments that you would bring to attack string theory? And then after that, I'll give you a chance to respond in your normal self. But I want you to be the best prosecutor now that you can be.
Well, one criticism of string theory is it drains resources away from other fields.
Yeah, but that's an operational one. I mean, I want to look at the physics of it. I mean, what are the criticisms? Certainly, if it doesn't work, it's draining everybody. I agree with that. But I want to look at the physics.
Yeah. So, could you rephrase that question? I misinterpreted your question.
Okay, sure. If you were the prosecuting attorney for those who think that string theory is not right and is the wrong way to proceed to find the theory of everything, what are the arguments that you would make to attack string theory? And then afterwards, I'll give you a chance to respond in your normal self. But right now, you're the prosecuting attorney against string theory, convicting string theory that it is wrong.
Okay. In other words, you want me to play devil's advocate. Is that what you're saying?
To yourself, yes.
Yeah. Okay. I think the strongest argument against string theory is the fact that it creates a multiverse of universes, but it doesn't select out our universe. The solutions of string theory, many of them have unstable atoms, unstable matter, so that the universe exists as a mist of floating electrons, floating neutrinos, and not much else. Stable matter does not exist in many of the solutions of string theory. So why should our universe be so special that we have stable atoms that create people, that create consciousness, that dream about these things? It didn't have to be that way. These other universes, some of them are chaotic. Some of them are random. Some of them have no stable matter whatsoever. And so the strongest argument would be that the theory of everything is a theory of anything, that anything that can go is a solution of string theory. So why should our universe be special?
So let's explore that. And this is the so-called landscape problem, where string theory looked like a definitive theory, but suddenly, a couple of decades ago, the realization was that because of the structural elements within string theory, there might be 10 to the 500th power of structures that one string theory would be. So it became this enormous landscape. But if that were the case, and the vast majority were inert or lifeless or sterile, that's okay, because the only place that you would be looking would be the place that you would be allowed to exist to look. And so the fact that we're special is not really that special.
Yeah, well, I'm not bothered by these arguments at all. Because first of all, if I take a look at Maxwell's equations of light bulbs or the equations of a laser beam, you ask yourself a simple question. How many solutions of Maxwell's equations are there? How many light bulbs? How many generators? How many hydroelectric dams? How many lasers can you build? And the answer is infinite. Forget about 10 to the 500. We're talking about an infinite number of solutions for light.
Is that the same?
It exists in all these forms. In other words,
is that the same thing? Is the infinite number of light bulbs as a result of Maxwell's equations the equivalent of different universes that come out of the structure of string theory?
Mathematically, yes, they are identical. People forget this. How many solutions of Maxwell's equations of light are there? An infinite number of solutions, depending upon how many light bulbs, how many generators, how many dams do you have? An infinite number. You see, each solution of string theory is a universe. That is the difference between string theory and Maxwell's theory. Every solution of Maxwell's theory is a light bulb of some sort. Every solution of string theory is a universe of some sort. But mathematically, it's the same thing. So the fact that string theory has an infinite number of solutions, which I believe in, forget 10 to the 500, I think it's infinite, is exactly the same reason why Maxwell's equations have an infinite number of light bulbs. Now, are you afraid of that? Are you disturbed? Do you go to bed at night saying, I can't believe in Maxwell's equations because a million light bulbs is the solution of Maxwell's equations? No, it's just the initial conditions. In other words, what you start with. The difference with string theory is we're starting with the Big Bang. That's the difference. And then we don't know the initial conditions of the Big Bang. If someone were to tell me right now the initial conditions of the Big Bang, I would find for you a solution of string theory which gives you that universe. So you see, I'm not worried about that, okay? It's philosophically very difficult to grapple with an infinite number of solutions, but we do that all the time. How many solutions of Newton's equations are there? How many tuning forks are there? How many rocket ships are there? An infinite number of rocket ships are possible. In the same way that an infinite number of solutions of Newton's equations exist, an infinite solution of strings also exists. The only difference is every solution of Newton's equation is a rocket ship of some sort. Every solution of string theory is a universe of some sort, but mathematically, it's the same thing. That's why I go to bed contented at night.
Well, I never go to bed contented at night because I have these conversations and I'm always disturbed. So that makes me happy though. So don't feel sorry for me. It's still not satisfying to equate a universe as a solution with a light bulb as a solution. But I promise I'll think about it. Um, what I'd like to do now is just kind of look at some of the implications or the meaning of the book, The God Equation, The Quest for a Theory of Everything. And let me just get your personal kind of observations about things. First of all, you seem sure in the book that we will find a theory of everything. Do you affirm that? Are you fully confident that that will happen?
I think, yes, it will happen. I think all the trends that we've learned about in physics always point to one thing: unification through symmetry. This is the fundamental theme of Mother Nature. All the forces of the universe combine to create simpler structures, unifying them through a simple symmetry, whether it's Einstein's four-dimensional symmetry or string theory supersymmetry. Unification through symmetry is the theme of the universe. And so why should the final chapter be any different from all the other chapters where we find these forces, we unify them, and we find that there's a symmetry when you unify these principles? That is the governing paradigm of the entire universe. And so I think that, yes, it will happen.
Michio, let me go with you. Let me say that I believe with you that there will be a final theory. But here's my question. Will that theory be contingent in that it could have been something else? Or is it of necessity in some sense, meaning that it could never have been otherwise? Philosophers use the term multiple worlds, possible worlds. Means that in no possible world could that theory have been different.
Well, Einstein used to say that the fundamental problem he grappled with was, quote, did God have a choice in making the universe? In other words, is the universe unique? Did it have to be that way? And I think the answer is yes. I think the answer is yes, because all the other universes that we play with are inconsistent mathematically. You know, in our universe, we know that 2 + 2 is 4. However, in other universes that we can create on a sheet of paper, 2 + 2 = 5, 2 + 2 = 6, and we throw them out because we know they're mathematically inconsistent. And why are they mathematically inconsistent? Because they contain what are called anomalies and divergences. These are the killers of anti-unified field theory. So many proposals have been made, hundreds of proposals have been made. Most of them can be killed off immediately because they have divergences, they blow up, or they're anomalous and violate some basic principle. And so, in other words, I think that the solution to the whole problem is unique. There is only one universe, only one equation, which is mathematically self-consistent, and 2 + 2 always equals 4 in that universe. All these other universes, you can get 2 + 2 is 5, in which case you can prove anything. Anything you want, you can prove once you assume that 2 + 2 is equal to 5. So I think that's why the universe, in that sense, is unique. Now, the number of solutions could be infinite, as in Maxwell's equations, as in Newton's equations. Newton's equations have an infinite number of solutions. That's why we have an infinite number of planets, infinite number of stars, infinite number of rocket ships. But the equation of Newton is unique. In the same way, I think that there's only one unique solution, because all the other solutions are anomalous or have divergences, and string theory is probably the only one, the example of a theory with no mathematical inconsistencies. So in other words, the universe had to be this way. It had no choice.
So we're talking about universes and that had to be this way in two senses. So let's be very clear. In one sense, the one theory that you think is string theory creates a total state of affairs. Let me use that term instead of universes. A total state of affairs of all reality. Everything that exists in any sense whatsoever is expressed and must be expressed by this one theory. But within that theory, the solutions or expressions can be an infinite number of universes. So each of those universes has the same equation underlying it, even though those universes will be radically different themselves and the vast, vast majority will be sterile.
I see what you're saying. Maybe the English language is not precise enough. Maybe we're talking about a metaphysics that is not just an ordinary physics, the physics of Newton, the physics of Einstein, the physics of Maxwell. Maybe we're talking about a theory of different physics, which is a metaphysics, a physics beyond physics. And that is the unifying principle. So what we're saying here is the principle is unique. The theme, the paradigm is unique. The solutions of this paradigm, there are an infinite number of them because there are an infinite number of rocket ships you can write down as solutions to Newton's equations. There are an infinite number of universes that you can write down, but the principle is unique. And what guides that principle? It has to be anomaly-free and divergenceless-free so that 2 + 2 always equals 4.
Michio, I want to explore some of your kind of broader thinking as has emerged from the book, The God Equation, The Quest for a Theory of Everything. You make the comment that I liked, but would like to hear you expound upon, that a theory of everything could be our salvation. You use the term salvation, a religious term, because physics in its traditional sense has a death warrant, your term, for the universe, however you define it, whether it could be the big big freeze as everything expands as the way it seems to be with accelerating expansion of the universe, so that ultimately you have the evaporation of all the black holes in 10 to the 100th or whatever years, and so you just have subatomic particles just floating around, and that's it. So it's the ultimate freeze. Or if you have a big crunch, which doesn't look likely, but if physics changes, and we do, then everything is squeezed together and destroyed. But you say a theory of everything could be our salvation from one of those two extremes, and that sounds like a radical expectation.
Right. Well, the most depressing paragraph ever written in the English language was written by the British mathematician Bertrand Russell in the 1930s, saying that physics says the sun will die. And when the sun will die, all the aspirations, the hopes, the dreams, the tears shed by generations of humans, it's all for nothing. Absolutely nothing.
The noonlight brilliance of our civilization. It was beautiful, a beautiful paragraph.
And that paragraph was written before the coming of rocket ships. And today, of course, we read that paragraph and laugh. We'll just leave the Earth. There's no law of physics preventing us from blasting off to another solar system. However, now we're talking about the death of the universe. That physics, the second law of thermodynamics, has within it a death warrant, that all equations show that the universe must eventually wind down, rust, decay, fall apart, whatever. And therefore, the death of the universe is inevitable. That's the second law of thermodynamics. But there's a loophole there. A loophole there because the second law of thermodynamics only talks about closed systems. If the system is open in hyperspace, there's an escape clause that billions of years from now will be so advanced that we'll have the Planck energy at our disposal. The Planck energy is the energy of the Big Bang. It's the energy at which space and time become unstable. If I have an oven and I could heat the microwave oven up to the Planck energy, what would happen? Bubbles would form. Not bubbles in water, bubbles in space would form inside your microwave oven, heated to 10 to the 19 billion electron volts. Each bubble is a gateway. It's a passageway to another universe. And so I think that when our universe dies, black holes dominate the universe, stars blink out, that we will create a bubble universe and go to another warmer universe and perhaps mess up that universe as well as messing up this universe.
You talk about finding meaning in the universe, and I know many physicists, when they deal with the implications of all cosmology, you go to the big freeze or the big crunch, and it looks pretty dire. But then people come up with, we can have meaning in our lives. We project meaning into the universe. These rationalizations, which I kind of resist. I like to face the reality. Steven Weinberg's famous remark, which when I spoke to him, he did not back away from, that the more we understand the universe, the more we see how pointless it is. And that's just reality, and just face it. You want to go beyond that to find meaning. Are you rationalizing?
Yeah, let me say two things about that. First of all, my parents were Buddhists. And in Buddhism, there is no beginning, there is no end, there's only timeless nirvana. But I was raised as a Presbyterian as a child. And in the Presbyterian religion, of course, there is the beginning of the universe with Genesis. So I've had two diametrically opposed ideas in my head. But there is a way to reconcile two diametrically opposed ideas. You see, Einstein says that our universe is a bubble. The bubble's expanding. That's called the Big Bang Theory. But you see, our bubble had a genesis. Our bubble had a beginning, just like the Bible says there was a beginning. But you see, our bubble coexists with other bubbles in a much larger arena. This larger arena is the hyperspace of nirvana. Nirvana, timelessness, a world beyond space and time. And so this is how you can reconcile Buddhism with Christianity, that our universe had a beginning. But other universes are being created all the time because of the quantum principle, because of inflation, which means that our universe expands into a larger arena. This larger arena is timelessness of nirvana. Now, what does this have to do with meaning for human beings now? Well, first of all, I think that if the universe is a chess game, there is a destiny to people who are watching that chess game. And their destiny is to, first of all, to figure out the moves, figure out how the pawns move and how the bishops and kings move, and then to become grand masters. So I think as far as the human race is concerned, I think there is a destiny there. Our destiny is to become grand masters of this cosmic chess game. Now, however, then people want to say, well, what about me? What about me as an individual, as a member of Homo sapiens? What does it mean for me? Well, I don't think that this one equation, the God equation, is necessarily going to bring happiness or fulfillment to people, because I think that meaning is something you earn. The meaning of life is to struggle for meaning that gives you meaning and substance to your destiny. It's too easy to have someone simply give you your destiny. That defeats the whole purpose of meaning. The meaning of life is the struggle, the process of struggling to attain a comprehension of your role in the universe. And so I think as a personal goal, don't look for an equation which is going to give you meaning. I don't think that's going to happen. However, I think that it's too easy for us to simply have a guru come from the mountaintop to give us the meaning of life on a platter.
Okay, let's go to your fundamental cosmology, as you put it, unifying the core thoughts of Christianity and Buddhism in terms of the creation of our universe, and then the embedding of our universe in a hyperspace of multiple universes. How does that work? I mean, all of that is very complicated. There's a lot of things going on in that fundamental reality. You have to have the laws of physics, if it's string theory, the equations of string theory. Then you need a whole set of other kinds of things that create this hyperspace or hypertime, this nirvana idea. It's not simple. How do you justify all of that as some fundamental reality? Where did it come from?
Well, first of all, it's a lot simpler than you realize. First of all, what is the net spin of the universe? If you look at the spins of all the galaxies and average them out, they all add up to zero. What is the net charge of the universe? If I add up all the plus charges to all the minus charges, they cancel out exactly. The net charge of the universe is zero. And what is the net energy of the universe? Well, matter has positive energy, but gravity is attractive and has negative energy, and the two cancel out to give you zero. So our universe came out of nothing. Our universe has zero spin, zero charge, zero mass energy. Our universe came out as a quantum fluctuation. Stephen Hawking called this the space-time foam. If you could have a super microscope, it can see down to subatomic distances. You can see that space and time is foamy, with bubbles popping out like a bubble bath. This is the multiverse on a small scale. You don't have to look in the heavens for the multiverse. The multiverse is inside your body. The multiverse is right here. In matter itself, we see universes being created and destroyed. These are called virtual universes almost instantly. And because of that fact, we don't see them. They're too tiny. But these universes pop into existence all the time. Now, our universe is special. For reasons we don't understand, it popped out of nothing and just kept on going and gave us the universe we have today. But our universe is mathematically, experimentally consistent with nothing.
Michio, the standard approach to why there is something rather than nothing by physicists is indeed this quantum foam and the emergence of particles and antiparticles, and they annihilate the vast majority of the time, but one time they may not, for whatever reason, you have universes developing, and that is certainly defensible. But it leaves open of the cauldron of bubbling laws of physics to make that all happen, whether in the one universe itself or, as you would have it, embedded within a hyperspace. So how do you deal with the mechanisms that created that something from nothing? You can't ignore that.
Well, the mechanism is very simple. There's an equation no more than 1 inch long that makes the whole thing work. Take a look at E equals mc squared. That unlocked one of the greatest secrets of the universe, the energy output of stars. Why does the sun shine? Well, it shines because E is energy and M is matter, and c squared is a very large number, and that's why the sun shines. So who would have thought that an equation 1 inch long could do that? Now, string theory is more complicated. However, you can summarize all of string theory into an equation about 2 inches long. In fact, that's my equation, string field theory, an equation that I wrote down years ago, which summarizes string theory, and it's only 2 inches long. It's not the final theory, however, because now we have membranes. And the field theory of membranes is turning out to be devilishly difficult. I'm working on it, many people are working on it, and we can't seem to get it quite right. But we know it must be there. So in other words, we know there must be a, quote, God equation that drives all of strings and membranes, and it's not so difficult. It's only, we think, 1 inch long. You know, English literary criticism every year gets more complicated, more books written about what did James Joyce, what did Hemingway really mean by that? Physics gets simpler and simpler every year. Why? Because it becomes more symmetrical. You can unify all these forces. And so all the laws of physics can be summarized on a single sheet of paper. That to me is stunning, absolutely incredible. The fact that all the equations that rule this universe of ours can be put on one sheet of paper. Of course, that sheet of paper is messy. We want to get it down to 1 inch, and we're not there yet. That would be the God equation. But you see, the universe didn't have to be that way. The universe could have been ugly. It could have been messy, random, chaotic, unstable. But here we are in this gorgeous universe. And that's why I think that what drives it is an equation equally gorgeous, equally beautiful, equally elegant.
You've chosen the core title, The God Equation, for your new book, and all the best with it. I enjoyed reading it very much. But let's now focus on that word God, because many physicists, when they use the word God, they use it in some Albert Einsteinian sense of sort of the order of the universe, whether it's not pantheistic, but just order itself is something that is remarkable and is so amazing that it's worthy of worship in some sense. So God is not a poor term in that sense. But in your book, you've actually gone further than that and have said that the elegant design of the 1 inch equation, which you expect, and indeed the laws of physics on your one page, you call it the strongest argument for the existence of God in some in some a normal religious sense, although you very clear that you yourself are an agnostic on this. But that's different than many physicists who would see the 1-inch equation as doing away with God.
Well, as Einstein said, science without religion is lame, but religion without science is blind. And I think that's true because science has to realize that there is something called philosophy, that there are philosophies in existence that guide scientific principles. Now, Steven Weinberg, a great physicist, Nobel laureate, perhaps facetiously wrote a paragraph in his book called Against Philosophy. And I read that chapter. It was a great chapter where he denounced the fact that philosophers always pontificate about the great theories of the universe, but never get anywhere, all amount to nothing, absolutely nothing. But that chapter is one of the most philosophical chapters that I've ever read. So here's a chapter called Against Philosophy, which is one of the most philosophical chapters that you can possibly write. So I think that scientists have gone too far. We have to intersect with where people are at in terms of their understanding of the universe. For example, in the 1990s, we had the Super Collider, bigger than the Large Hadron Collider, to be built outside Dallas, Texas. It was canceled. In the last day of hearings, one congressman asked the physicist, he asked him, quote, "Will we find God with your Super Collider? If so, I will vote for it." Well, the poor physicist didn't know what to say, so he said something like, "We'll find the Higgs boson." Well, the vote was taken. A multi-billion-dollar machine was canceled. The Congress gave us $1 billion to build a hole for the machine, canceled it, and then gave us a second $1 billion to fill up that hole. $2 billion to dig a hole and to bury it up. Since then, we physicists have batted our heads asking ourselves, how should we have answered that question? Will we find God with your machine? Now, I don't know about other physicists, but I would have said this. I would have said, God, about whatever signs or symbols you ascribe to the deity, this machine, the Super Collider, will bring us as close as humanly possible to his greatest creation, Genesis. This is a Genesis machine, which on a small scale will reproduce the most glorious event in the history of the universe, its birth. Instead, we said Higgs boson, and our machine was canceled, and American physics was set back 2 generations as a consequence.
Maybe you should run for Congress.
Well, just realize that we physicists have to learn to sing for our supper. That we have to realize that taxpayers are going to pay for the machines we build. During the Cold War, we used to just say one word to get funds. One word to Congress. We would say Russia. And then Congress would come back with 2 words. How much? Well, those days are gone. We can't do that anymore. We have to engage the public to speak the language that people speak. People want to know about meaning, about their role in the universe. Well, I think scientists should address some of these questions rather than hiding in the sand.
So ultimately, I want to ask you this as a final question. If you were asked what exists, what are the most fundamental elements of existence, however many categories you need at that most fundamental level, from which you can build the entire state of affairs that we find ourselves, whether it's multiple universes, hyperdimensions, or what are those fundamental categories of existence that cannot be reduced one into the other?
Well, that's a tough one. First, you have to have an arena, a stage in which things can happen. And then you have to have the players to make things interesting. But one of the criterion for the players is something that we forget totally, and that is stability. It is incredibly difficult to create stable universes. Take a look at Newton's theory of gravity with planets going around stars. That is extremely unstable. Most solar systems in the universe fall apart. Comets collide, planets collide, things go plunging into the stars, unstable. Newtonian physics is fundamentally unstable. You know, many people say, we don't need Einstein. We don't need the quantum theory. Newton is common sense. Let's just believe in the Newtonian forces and forget about Newton, forget about Einstein, forget about the quantum theory. Wrong. Newtonian physics is unstable. Orbits are unstable. How do we stabilize them? Well, in the quantum principle, we stabilize them in a way that blows people's minds away. We stabilize the atom by making electrons be two places at the same time. Now, you may say to yourself, that's crazy. Crazy. Well, in chemistry class, high school students call them orbitals. Remember we had to struggle with orbitals? What the hell is an orbital? An orbital is not an electron cloud circulating around an atom giving rise to oxygen and carbon. No. An orbital is an electron being many places at the same time. So in other words, the solution to stability of Newton's equation is to create parallel universes. Think about that. A simple philosophical argument. Why is matter stable if Newtonian orbits are inherently unstable? And the answer is the quantum principle. But the quantum principle means that you can be two places at the same time. Now, if you don't believe me or you don't understand what I just said, get used to it. That's the way the world is. Sorry about that.
We first started speaking some 14 years ago. And if we asked each other if we were now 14 years from now, if we were, just to pick a date, 2035, and we were having this conversation reflecting back on what we talked about today, what do you think we'd be talking about then?
Well, it's my fondish wish that in our lifetime, we would see the final theory. However, of course, history and science have a time scale and a clock of their own. We are humans. We have human desires. We like things completed in our lifetime. But, you know, it goes back to the Middle Ages. During the Middle Ages, architects would build cathedrals knowing that maybe their grandkids would complete them, that they embarked upon this grand journey to glorify God. It would not happen in their lifetime. It's possible that it may not happen in my lifetime because the theory is smarter than we are. I like to think of it as wandering in the deserts of Egypt and one day stumbling upon a rock. Well, you brush away the sand and you find that it's the top of a pyramid. And over the years, you brush away the sand and you find layers and layers of hieroglyphics, layers and layers of arcane languages and equations and an alien intelligence. And finally, after so many years, you finally are at the ground floor, about to open the final door to the pyramid. I think that's where we are now. I think we're very close to opening the final and last door to this great pyramid, which may be the theory of everything, or maybe the theory of nothing.
Well, I look forward to checking back with each other every so often. And certainly 2035, you have an open invitation for another conversation. But lots in the meantime as well.
I look forward to it.
Want to ask your own questions of the world's leading thinkers? Closer to Truth members can join exclusive live conversations and submit questions to be answered in real time. Visit closertotruth.com to register for your free account.